So I'm recording a short micro lecture here on furthering the work that we looked at with imperative programming, and specifically what we can do with it, because we built up some tools and now I want to show you why we have those tools. And one of the things that we can do is we can start writing proofs. We can prove certain properties about the language that we're working with. So one of the properties we will look at is a proposition towards proving the determinacy of the language, to make sure that you don't have kind of arbitrary execution and randomness built into the execution model of your language. So all of this work is out of the PDF that I attached on Piazza. It's page 14 or so, and the PDF walks through a lot of the same stuff that we will be talking about, including many of the same steps. And this is the property that I want to prove. This is P. So we want to prove that for every command that we have, that is assign, skip, if, while, and sequencing, and for all states, then if we have some command with some state, and that small step transitions to C1 and C2, and it also can transition to C2 and S2, then C1 must be the same as C2, and S1 must be the same as S2. So the purpose here is to say you cannot transition to two different states or two different commands. No matter what transition you take, it will always lead to the same place, which is the equivalent of saying there's exactly one small step to take at any point in time, and if you take that one small step, then you will end up in the same place no matter what. So how can we prove this? We're going to do what's called a structural proof, where we take a look at the different cases that can exist here. So it's a case analysis as well. And we can look at the 5 different commands that exist within our language. The first one is skip. So first we can say, for skip with S, does this property hold? Well, here it's actually just vacuously true, because it's impossible to ever take a small step from skip. Skip is our done command. That's saying there's nothing left to do. So, okay, it holds, because we can't ever have C1 or C2. Neither would ever exist. The second option we have is the assign command. So we could say, for example, that some L is equal to some value N. We might say that X equals 3, for example. And then we want to show that if we have X equals 3, there is only one possible way that we can represent that and take actions based on that using our semantics. This actually follows quite straightforward from our rule that we have. So with assignment, we say that if we have some expression with some state, that's always going to evaluate to N, and we have the command L is equal to the expression with the same state, then that transitions to skip and the state where L points to N. This is the only rule that we have for assignment, which means that we need to take this step no matter what. And so long as we accept that the premise is deterministic, which at this point we will just make that assumption, then we will always end up in this final state. And in the first case, we will end up with skip and S where L points to N1, and in the second we have S where L points to N2, and because of the determinism that we've established up above, N1 will equal N2, therefore we have S1 will equal S2, and skip is equal to skip. So somewhat informal, but not too hard to follow in terms of seeing that we only had one rule to apply. When we apply it with the first C1, S1, so we could say that C1, S1 is equal to this, and C2, S2 is equal to that, we end up in these two states, and those two states must be equivalent because there was only one way to get n. These are our two base cases. We have skip as one base case and assignment as a second base case. Next, we're going to look at what happens with our more complicated cases, and here we have to use induction to help solve these. So next up, I want to prove the property holds for sequencing. That is to say, we have some command D1 and a second command D2 to execute after it. And like I mentioned, we're going to use induction here. What that means is that we are assuming that our property P holds for D1 and also that our property P holds for D2. And we get to use that to our advantage when we solve the rest of this. So in the first case, we have that D1 could be skip. And there's one rule that we can use if D1 is skip. That rule looks something like if we have skip and then some command C with some state, that is going to transition to the initial or the second command in the state. So we can take this rule for both of our paths here, and in the C1 path, the C1 S1 path, we would have that. So just to show what this would give us, we could take this path and we would end up in some state that looks like D2 prime and S, because state doesn't change. And in the C2 path, we would have D2 double prime and S. But notice D2 was the same D2 in both cases. We didn't actually change what that value was. So we know that D2 prime is the same as D2 double prime, which is actually the same thing as D2 in the first place. And because our property holds on D2, by our inductive hypothesis, we know that we are successfully in the same state, that we have C1 is equal to C2, and S is still equal to S in this case. So this is one of the possible scenarios for sequencing. The other option that we have is that D1 is not skip. And if D1 is not skip, then we have a different rule that we can apply. And that rule says that if C1 with some state transitions to C1 prime with some state, then C1, C2, S will transition to C1 prime, with some new state, S prime. C1, C2 with some state S will transition to C1 prime, C2, S prime. Basically, we take this small step here. And we can apply this rule to both of our branches, our C1 branch and our C2 branch. So in the case of C1, we would be saying that we can transition to some state C1 prime, which would be D1 prime. So by applying our rule, we could end up in a state that would look something like D1 prime, D2, and S prime, S1 prime. And then in the C2 case, we would be saying that we have some different D1 prime, so D1 double prime in this case, D2, and S2 double prime. But again, we get to use the inductive nature of our problem, where we've assumed that our property holds for D1. And if our property holds for D1, that means that up above, our premise must have provided us with the same C1 prime and S prime. And that means that this D1 prime and D1 double prime must be equivalent. And additionally, that S1 prime must be the same as S2 double prime, which I could have called just S1 prime, perhaps, or just S prime. And what that shows us then is that if D1 prime and D1 double prime and S double prime are equivalent, then C1 equals C2 and S1 equals S2. And this allows us to show that the property holds for sequencing. Now I'm going to stop here, and you can check the PDF to look at the proof for the while command as well, and then solve if on your own if you'd like.